A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Today we'll be talking about metal oxide field effect transistor. This lecture is a part of lecture series from the course of Introductory Electronics, having the course code of PHY201. In today's lecture, our basic objective is to understand the metal oxide field effect transistor. We also need to know the different types of field effect transistor, and finally we need to know the structure and operation of metal oxide field effect transistor. It's normally is also called as MOSFET. The first thing we need to know is the different types of field effect transistor. There are mainly two types of field effect transistors. One is called as junction field effect transistor, which is simply called as a JFET, and the other is called as metal oxide field effect transistor. Metal oxide semiconductor field effect transistor, that is called as MOSFET. So first we need to know the junction field effect transistors, JFET. The structure of junction field effect transistor is clarified here. We have two things, one is the source and other is the drain. The current flows in between the source and the drain. And the gate, here is the gate. The gate is used to control the width of the channel. Keep in mind, this is channel, so this is a type of N channel junction field effect transistors. So with the help of gate and with the help of this potential difference, we can control the width of the gate, and resultantly the magnitude of current that is flowing from source to gate changes, because if the width increases, so the magnitude of current increases, and if the width decreases, then the magnitude of current also reduces. So this is a simple structure of junction field effect transistors, and all these things are grown on a substrate. Let's come toward the metal oxide field effect transistors. This is the simple structures of metal oxide field effect transistors. Here is the source, here is the drain, and this is the oxide layer on which the gate is made. So just below the gate there is oxide layer. It is normally made from SiO2, and all these things are grown on a silicon substrate. There is a silicon channel just below the oxide layer, so even the drain and source is also on this silicon layer. So this is the simple structure of that, and in which the current flows in between the source and drain. This is the other view of the same metal oxide field effect transistors. So this is actually the gate to control. This is the length of the gate. This is the drain, to which we need to receive the current, and this is the source. So this current flow from source to drain, and this is actually the channel through which the current passes. So this gate is used to control the magnitude of to control the width of the channel. Resultantly, we can control the magnitude of current. Let's come toward the other type of field effect transistor, that is called as MOSFET. MOSFET is metal semiconductor field effect transistors. So in metal semiconductor field effect transistors, metals is also used, and the gate is formed by Schottky barrier to the semiconductor layer. So the gate channel insulator consists of the depletion region. Is the same like the material as the channel. The nature of the material is the same like channel, and this structure is very similar to junction field effect transistors. Here, if we look toward the structure, here is the source and here is the drain. So the current flows between source and drain, and here is the gate to control the magnitude of current, and this is the channel through which the current passes. This is N channel junction field effect, metal semiconductor field effect transistors, and this is actually the substrate on which everything is grown. Let's come toward the basic structure of MOSFET, that how the different parts is made and what is the role of each part in this structure. This source and drain and even the gate all are made from is a type of metal contacts. So this is a metal contact with the surface, even for the source and for the drain and for the gate. This part is a type of insulating layer. It's made from the insulating layer that can control, and this is the p-type substrate that is made from that. So this is a p-type, and this is actually the channel or the path through which the current passes. So we can control the width of this channel with the help of this gate. The external potential difference due to the gate, we can control the width of this layer, and the current can flow through it. So if the width increases, there is more ways for the current to move, and if the width reduces, so the current could be controlled. So the gate electrode is placed on top of very thin insulating layer, and there are a pair of small n-type region just under the drain and source electrodes. You see, if we apply a positive voltage to gate, it will push away the holes inside the p-type substrate and attract the movable electrons in the n-type regions under the source and drain electrode. So in this way current can flow from source to drain. This is further explanation of the n-channel MOSFET. So if we increase the positive gate voltage, so what happen, it pushes the p-type holes further away and enlarge the thickness of the created channel. So as a result, increases the amount of current which can go from source to drain, and this is why this kind of transistor is called as enhancement mode device. So it can use for as an enhancement mode device for this particular purpose. So the structure is again the same what we had observed in the last slide. Let's coming toward the cross section and circuit symbols of an n-type MOSFET. Again, this is another view, and the source, it is connected with the sources. Here the symbol of the MOSFET is also explained. The symbol of the MOSFET is a bit different from the general transistors. So we have here the source, and here we have the source, and here is the drain, and this is the gate, and everything is grown on a substrate. So the gate is used to control the magnitude of current. If we look here, we have, this is the source, and this is the drain, and this is made from n-type. This is also, drain is also made from n-type, and this is the gate, is connected with the potential difference. So gate is normally placed on oxide inversion layer, and this everything is developed, or it is grown on a p-type substrate. So this is actually the other. So we would like to enhance more knowledge regarding the MOSFET. So this electron, when it moves in between the source and the drain, so this behaves in a similar way, but they passes current when a negative gate voltage creates an effective p-type channel layers under the insulator. So by swapping around p-type for n-type, we can make pairs of transistor whose behavior is similar, except that all the signs of the voltages and currents are reversed. So pair of devices like this are called as complementary pairs. So we can also create the pairs with the help of this type of combination of the transistors. So let's come to the other explanation of this and the 3D view of this metal oxide field effect transistors. Here is the gate that is grown above. This is the 3D view, and this is the source and drain. Both are it's made from p-type of material, so it means is a type of the majority carrier in this region is a hole and the minority carriers are electron. In the last case we consider this for the n type, that was like this. Let's come to the previous case. We have considered that both source and drain that were made from n type of material, but here we are studying for p type of material. Here if we look, the source is also made from p type, and drain is also made from p type, and this is developed on n-doped substrate. So the gate is here. So what happened again, when we connect it with the different polarities, so the current flows, but the current in this case will flow in the conventional way. Here this is the source, it will move from source toward the drain when this system is connected in a circuit, and this is the sample representation of that. So all these things are grown on a n-type substrate. So if an n-channel MOSFET, the channel is made of n-type semiconductor, so the charge is free to move along the channel or negatively charged. For the case of n-channel semiconductor, n-channel MOSFET, we have electron as a majority carrier. Keep in mind, field effect transistors are also called as unipolar junction transistor because it's only the majority carrier can play the major role. So only the majority carrier. But if we look toward the BJT, that is also called as a bipolar junction transistor because both electrons and hole can contribute to the current, and we can control the magnitude of current with the help of both holes and electron. But in this case only a majority carrier will contribute, just like if we consider for n-type semiconductor, n-channel MOSFET, the electron or the negatively charged particles are responsible for the carrier, for the current, and that is why only these are used. But if we consider a p-channel device, that is a p-channel MOSFET, so the free charges which move from end to end are positively charged particles, and that are actually the holes. This is a simple illustration of the behavior of a typical complementary pairs of power MOSFET made by Hitachi for use in HI and FI amplifiers. So the curves are drawn between currents and the voltages, and its behavior is observed how it behaves. This is the sample for n-channel MOSFET, and this is the sample for p-type MOSFET, and this is complementary overview of the current and voltage between the different MOSFET. So here n-channel device, we apply positive gate voltage to allow source drain current. With a p-channel device, we apply a negative gate voltage. So as means there is correspondingly looking toward the p-type and n-type channel, we can correspondingly change the polarity and move the current, but keep in mind the current will often move from source to drain, and we can control the magnitude of current with the help of gate. We have structure and principle of this metal oxide semiconductor field effect transistor. This is the top view of the n-type MOSFET. Here we have source and drain, and the gate is here, so it's connected to the external potential difference, and the current and the polarity is also shown. This is actually the width of the gate. So the gate length L and the gate width W is also present, clarified. This is the width of the gate. The length L does not equal to the physical dimension of the gate, but rather the distance between the source and drain regions, and the overlap between the gate and the source or the drain region is required to ensure that the inversion layer forms a continuous conducting path between the source and drain region. So typically this overlap is made as small as possible in order to minimize its parasitic capacitance. So the structure is made so that the overlap is like this. The source and the drain overlap, or the gate is like this if we look from the top view. This is the other structure of the more detailed structure of the MOSFET, and this is actually the motion of the charge carrier which are responsible for the channel. We have here is a source, and again this is n channel MOSFET. Here is this is the source and this is the drain, and this is the SiO2 layer actually that is made of. So this is actually the gate that is if we take a side look, so this is just above the channel, so it can from upper side it can control the width of this channel, and with that we can use there. So we have basically it is a 3-terminal device. There are 3 things that are they play main role. One is the source, other is the drain, and the third one is the gate. And we have, for this purpose, we have the gate voltage and the current, and gate control the potential barrier, and that is actually act as a resistor, but as a variable resistor. It is acting for controlling the magnitude of current. Drawing the IV characteristic for the MOSFET, we have this value for the low drain voltage, where we have is a type of relationship of direct relationship between ID and VD. This is for low drain voltage, and in some cases when we have point P that is indicated so the pinch off we have a pinch off point where we can control the pinch off point. This is a pinch off point that is here we have this is actually the channel there. So this is a pinch off point, and we have saturation, and then finally we can draw the when the width of the layer increases due to the gate, so we can get saturation current, and that is actually beyond saturation, where the width has, if you look toward this figure, the width is more and now, so therefore there is high path for the carrier to move, and as a result we can get saturation current. So this is actually beyond saturation curve for the IV, that is the drain current and the drain voltage. We have different type of MOSFET that is used, and we have n-channel enhancement mode of this MOSFET, and it is the basic output characteristic of that between the ID and VD, and this is the transfer characteristic for that. And we have n-channel depletion that is normally on, and this is the curve for that. Here this region n-channel is on, so current flows in between the gate and source and gate, and this is for n channel, both for n channel, and in this case it is off, and this case is on. Now come toward the P channel enhancement, that is normally off. In this case, this is actually the channel is made from P type of material, but this region is normally off. So if we look toward the IVD and on a curve between ID versus VD, so that is like this, you see. For different values of VG, that is the gate voltage, we have these values. And coming toward the P type P channel depletion, that is normally on. In this particular case, we have the curves that is like this, so we can get positive, we can get these values, and this is on the other side. So this is the curves between the ID and VD for the P channel depletion, that is normally in switch on mode. We have the different mode of the MOSFET, just like we have enhancement mode, just like we have in junction field effect transistor, and in field effect transistor we have different mode. In the same way, we have different mode for MOSFET. We have enhancement mode where maximum we can here this is an enhancement mode with this configuration. This is also in enhancement mode Keep in mind this is for N channel MOSFET and this is for P channel MOSFET. Both are in an enhancement mode, and other is the depletion mode. So just like the depletion, the width of the depletion layer increases. So this is the depletion mode of the N channel MOSFET, and this is the depletion mode of P channel MOSFET that is made for this particular case. The channel length, we can change the channel length, and this could be changed with the help of a drain gate voltage, but physically this is actually in this case is made from SiO2, and that is the short channel which is less in size. If you look toward that, that is less than 1 micrometer, uh, and is effective channel length that is used for the motion of carrier in between the source and the gate. Trying the voltage scaling between the channel length and the width, we can see that in some cases the threshold voltage is the behavior of threshold voltage is like this, but the supply voltage is like this, not threshold voltage, but for the supply voltage behavior is like this. I means increasing the channel length can lead to the increasing the voltage can lead to the increase in the channel length, or vice versa. Some materials or new materials are used for this scaling, and early 1980s the material used for the anti-grating MOSFET on silicon substrate have not changed greatly. So the gate metal is made from highly doped polycrystalline silicon, and the gate oxide is silicon dioxide. So for the smallest device, this material will not be replaced. So this is the simple illustration of the illustration of the silicon transistor that is used for that, and the simple silicon on insulator MOSFET that is similar to the traditional MOSFET, that is a bit advanced in the technology in the field of MOSFET. So this is something about the metal oxide field effect transistor, and I hope we can have some new lectures in the upcoming slides. Thank you very much.